third paper for this session is Combinatorial RL-based scheduling for pipeline edge TPUs. And it will be presented by Jiaqi Yuan, University of Utah.
Hi, everyone. I'm going to talk about my work, combinatorial RL-based scheduling for pipeline edge TPUs. Reinforcement learning has been applied to many combinatorial optimization problems, such as the constraint-based solving, planning, and hardware design automations. The DN model scheduling is a classic combinatorial optimizations. And it's well known that DN model scheduling results can affect the edge device runtime performance significantly, which can be verified from our ResNet 50 evaluations, which is based on 9 different scheduling solutions. For example, we can see that the scheduling solution 7 has a runtime performance degradation of 32%. Besides, we also observed that the scheduling solution provided by edge TPU or feature compiler still have a lot of room to be improved, which motivates us to explore the reinforcement learning scheduling on edge devices and use the Google edge TPU as our scheduling backends. This figure illustrates several widely used graph scheduling algorithms. The heuristic method can solve the problem with several seconds. However, the solution is non-optimal. In the contrary, the exact method can generate the optimal solution with a high solving runtime overhead. In general, an ideal case of scheduling should provide near optimal solution with a low solving runtime overhead. Because reinforcement learning can imitate the behavior of the exact method and with short inference runtime, so we decided to use the reinforcement learning as our scheduling method. This is our scheduling formulation. The input will be a DAG, the computation graph, and the scheduling constraints, which contains the data dependence and resource constraints. The output objective will be an exact scheduling. All of the nodes in the computation graph will be assigned into a given number of stages. The input information will be embedded. The embedding contains 3 important attributes: the absolute coordinates, relative coordinates, which is data dependence, and every node's topological level, and the node's attributes. It contains the memory caching and communication cost. After the inference, we finished some post-inference adjustment to match the hardware domain knowledge. This is our LSTM-based point network framework. It contains the encoding and decoding components. The encoder digests the embedded information and transforms it into context information. With the context information, the decoder generates the probability distribution over all nodes in the computation graph node. We train our model with gradient policy. The reward function is a cosine similarity, which is shown in the red equation. The cosine similarity measures the similarity between the model output and the ground truth label. One of the main challenges of RL work in the area of optimization is the lacking labeled data set, and the RL formulation enables us to use the synthetic data only and still be able to generalize our problems very well. So we randomly generated our nodes attributes, such as the memory caching and etc. All of the label is generated with exact method. With the synthetic data set, we can full control of graph complexity without massive data collecting, because it's time-consuming. This is our experimental setup. we use the integer linear programming as a representative work of the exact method, and we use Google Edge TPU compiler as the representative work of the heuristic method. Let's take model DenseNet 201 as an example. Compared with exact method, our work improves the scheduling runtime 140% with only 1.1 inference runtime degradation. You can see in here. And this is compared with the heuristic method, we improve both of the scheduling runtime and the inference runtime significantly. Thank you for your attention. I would be like to answer your questions.
Yes. How many how many nodes have you tried for now? Like
in the computation graph nodes?
Yes.
Yeah, basically 100 nodes to 200 nodes.
Okay.
It's we tested, we generated pretty much half millions computation graph, and its nodes it should be from 100 nodes to 200 nodes.
Okay. And what, like when you scale this, what are the bottlenecks you're like usually seeing?
What I'm saying?
Do you see any bottlenecks when you scale up the system?
Yes, because our work is using reinforcement learning, so we can extend our work to, I think it should be work for a pretty large computation graph, like 500 to 600 nodes. Yeah.
Okay.
But we also tried several exact method. The bottleneck should be 200 nodes. If the computation graph is larger than 200 nodes, it will be consume a lot of time to solve the whole problem.
Okay. Yeah, I think that's all from every one of us. Thank you so much for presenting, Jiaqi.
And we are very thankful for our sponsors. The premier sponsor this year is Edge and Pulse. And then executive sponsors are ARM, DeepLight, Qualcomm, and Syntiant. Platinum sponsor, Analog Devices, BrainChip, Infineon, Clickertech, Latent AI, NXP, Reality AI, Renaissance, Sony Semiconductor, and Synaptics. Really very diverse company, great companies who are really driving tinyML forward. Gold sponsors for the Hub, Micro AI, Prophecy, Seed Studio, SenseML, ST Microelectronics, SynSense, XMOS. And we have a list of civil sponsors: Yuan Devices, Aspinity, Seva, EMSA, Greenwave Technologies, Grovity, Hymix, HOTG, Imagimob, ITMIS, Lattice, Nota, OmniML, PixArt, Plumerai, Kixo, Rachner, Rixen, SAP, StreamAnalyze, Texel, and Google. So we are very thankful for their support, and more importantly, for them being part of this community and driving it forward.